Hello, vintage computer friends. In my last video I gave you a demonstration and deep dive into the Kosmos CP1 1983 educational computer from West Germany. And in this video I want to give you a demonstration of the Busch Microtronic from 1981. Both machines are quite different, and we are going to implement the same program that we implemented on the CP1 in my last video. So, quick reminder, we implemented a program I called Sigma I for obvious reasons. What it does is it simply computes the sum of the first n natural numbers, right? So for n equals 0, you expect the result to be 0, and for n equals 3, you expect the result to be 3 plus 2 plus 1 plus 0 equals 6. And of course it's very simple to implement using an iterative algorithm, a simple loop, right? So you need two variables, a counter, which you initialize to your target value, your n value, in this case 3, and this sum variable that keeps track of the sum computed so far, right, for accumulating the sum. Then in the loop, basically, you add the current sum and the current counter together, store this in your sum variable, then you decrement the counter by 1, right? If your counter has reached 0, then you are of course done with the loop, and all what's left to do is you display the result on the display. Else your counter is still greater than 0, then you need to do one more round until you reach 0, right? Or I mean, you could also terminate when you reach 1, of course, right? But then you wouldn't be able to compute the sum for n equals 0, depending on whether you consider 0 a natural number or not, right? So, and I showed you how to implement this on the CP1 in its machine language. And I also had a couple of comments and some criticism. So it would have been possible to put the address here in hexadecimal and then basically 4 digits instead of 5 for the opcode, right? So opcode type basically and operand, right? If they only had used, hexadecimal. And the Microtronic does it exactly like this, right? So if you look at the display here, you see that given that the opcodes are only 12-bit on the Microtronic, indeed 3 hex digits suffice to display the opcode, right, the instruction word. Here we would have needed 4 digits, right? But you can see that the Microtronic is indeed capable to display the address while we are inspecting the program with the memory, right? And whereas here we always need to ask for the current monitor address basically, which is of course a bit tedious using 9 out, and I also suggested it would have been good, to at least have a key basically similar to these buttons which simply display the accumulator or program counter on request, right? It would have been nice to also have a key for the current monitor address instead of having to type 9 out all the time. Okay, but that was the last video, right? And in this video I really want to show you how to implement the same program. Sigma I is a summation program, right, of the first n natural numbers on the Microtronic, which has a different architecture. It's a Harvard architecture. And whereas the CP1 is a theoretical, very pure mathematical von Neumann architecture, right? Alright guys, let's get started. So I have a printout of the program here, right, and I'm going to enter this and explain the different opcodes and the instructions, right? So as I said, I mean the Microtronic is a completely different beast, right? It has actually 32 4-bit registers, and all the registers have numbers, hex numbers from 0 to F, right? So you always have one set available basically, the current register set, right? 16 registers of 4-bit registers, but then you can also basically exchange the variables with a set of background registers. So altogether this machine has 32 4-bit registers, and those registers, they are organized in banks of 8 registers. So there's a lower bank and the upper bank, right? And what you can do is you can basically swap in, exchange the current register set with the background register set in the lower bank, or only do this for the higher bank, right? Or you can also swap the banks basically, background and foreground register banks. So, but let's start entering the program. So we need to use the registers now in a clever way, right, in order to create a result which is obviously more than 8-bit in general, right? And so on the CP1 we only use 8-bit because it would have been difficult to overflow the result, right, when it got greater than 255. So there's no carry overflow, right? So actually the CP1 gives an error if a register value is greater than 205 or if it's smaller than 0, right? Over and underflow, there are no carry flags for this that would allow you to then, use that carry flag to overflow into another memory cell, right, or register. So on the Microtronic you can do this, right? So the first thing is we are clearing all the registers. So F08 means clear all registers, right? And so now you see that the monitors advance the address. So the next thing we want to do is we want to display 2 digits on the display, registers D and E. So F means display, right? And 2 is the number of digits that you want to display on the register. So it starts on the right. You can display 1, 2, 3, 4, 5, up to 6 digits, and they have to be consecutive registers, right? So if you start at, like here, at register D, then you will display registers D and E, right? But you can also say, for example, F60, then you would display registers 0, 1, 2, 3, 4, 5 from right to left. So that way you already have, more control, much more control over the display than the CP1 offers, who can basically only display the accumulator, right? Or of course the content of a memory cell if you loaded it into the accumulator first. And it can only display a value from 0 to 255, whereas the Microtronic can actually take full advantage of all 6 digits and display individual independent hex numbers in there, right? So that's of course a big advantage. Next thing we want to do, and this is also something we could not do with the CP1, right? We want to input now basically the n value, right? 0, 3 or 10 or 20, right? Up to which we want to compute the sum. So basically the variable argument n for our big sigma program, right? And that we can do using keyboard input, right? So something that the CP1 also does not support, right? So as I said in my last video, there's no instruction, no opcode that allows you to read in a value like a byte, right, from the keypad at runtime. So you always have to use the monitor to either load a constant, right, or to prepare a memory region, right, and then load that value into the accumulator from that memory cell region, right? Or you can use the GPIOs basically, but then you are limited to basically 8 digital buttons, right? And I mean, good luck, programming something that emulates basically in that way a keypad, right? Very tedious. Whereas here we can now, we want to enter basically a 2-digit decimal number, right? And we have keypad input, right? And so now I talked a lot, I lost track of where I was. So we want to continue at address 02 and enter basically one value, one hex 4-bit digit into register E. FF is a kin or keyboard input, right? And E is the destination register. So we have our first, the 10 value of our decimal input, right? There, right? In the E register, and we also want to input the 1 position of the value, right, in the D register. So now all the arithmetics functions, Microtronic is a hexadecimal machine, right? So if you input something, decimal, you got to convert this into hexadecimal and then do arithmetics with this, right? And for this we have a special conversion instruction, right, which is called F04. And what F04 does is it converts the 3-digit decimal value in the register DEF, hundreds, tens, and ones, right, into a hexadecimal representation, so that we can then use the addition opcodes basically to work with this, right? So if we input 06, then of course it's still 06, right? But if we input 15, then we would have 1 in E and 5 in D, right, from our keypad input that we just entered, and then F04 would convert this into F00, right? And then we can do arithmetics with it. So now after this we have a hexadecimal representation of our n value, right, of our count, and initialize our counter to this. Now what we want to do is clear the display, turn it off, right, because otherwise we will see, you know, stuff going on from the summation and so on. So we want to turn off the display. Also the machine runs much faster then, right? Similar to maybe something like the Sinclair ZX or Timex 1000, Sinclair ZX81, Timex 1000. If you turn off the display, the machine runs faster, right? In this case, because the TMS 1600 microcontroller doesn't need the time to multiplex the display, right? So and now we actually are in the loop, right? So now we want to implement this addition. So current sum plus current counter, right? And we are going to use the hexadecimal value of the counter here, right? And count down basically from registers D and E. And for the sum, we are setting aside a number of registers here. So let's keep it 8-bit. So we are going to chain registers 0 and 1 and 2 together. And because number 0 we use for waiting for keypad input and so on. So the first thing we want to do is we want to add the 1 location of the counter to our sum, right? And so 1 and 2 are the sum registers now, and for this we have an opcode 4 for add, and then source register D to destination, right? So we are adding the counter value, the 1 position, to the 1 position of the sum. And now it is possible that this of course now overflows, right? So if we already had F basically in 1 and now we add another 1 or 2, then of course this register might overflow. On the Kosmos CP1 you get an error then and the program stops, right? On the Microtronic you actually have a carry flag which is being set, right? And the register loops around, right? So it starts 0 again, modulo 16. And you can then use the value of the carry flag to actually add another, to add the carry flag, right, the overflow to the follow-up register, and we are using the register 2 for the 10 position, right? And actually, given that it's hexadecimal, it's the 16 position, right? So, and the opcode for this is FB for carry overflow, and then into register 2. But then, of course, we also still need to add basically the 16 position, right? The second position, which is of the counter, which is in register E to register 2, right? And which is then 4E2. Source is E and destination is 2. And yeah, so let's keep it to 8-bit in this example. So we are not going to overflow to a third register here, right? And that of course makes it comparable then to the CP1 version, where the maximum result also was bound to 8-bit because of the accumulator 8-bit, right? And so we got this now for E2. Where are we actually? Here, right? And then it's time to decrement the counter. And this is very easy because there's an immediate subtraction operation. 7, 1. 7 means subtract immediately, and the constant is given, right? 1, and you want to subtract D. Now, this might result in an underflow now of D, right? If D was already 0, you subtract 1, you know, you have an underflow, and then you got to subtract 1 from the next higher position register. The 16 position is an E. And again, we now have a carry underflow operation here, which then subtracts, if an underflow happened in the D register, we can automatically subtract 1 from E, right? So we perform the underflow to the next value position, and that way you can really chain together registers of arbitrary lengths, right? You can basically implement a, you know, a counter as big as you have registers, right? and of course that exceeds more than 8-bit, right, which you have on the CP1 as a max, right? So this is a very versatile programming model, and very powerful also. So great jobs there, Busch. And yeah, now we want to check if the counter reached 0. For this we compare first the 0 position, sorry, the low digit position of the counter if it's 0, and 0 means compare with immediate value, right? So and we are comparing if D is now 0, right, using 0. 9 is compare immediate, 0 is the immediate value to compare to, and D is the source register which you are comparing, right? And if it is not 0, right, in this case a flag is set, and we can branch basically conditionally. So if it's not 0, then the carry flag is set, right, and we branch to the beginning of the loop, which is here at address 6, right? So in that case we know, we are not done with the loop, right? But of course we also gotta now check the next highest register, which is E, if this is 0, right? And for this we are using 90E now, and again, if this is not 0, then the carry flag is set, right? It's greater than 0, and then again we also need to continue with the loop. Else we are now at the end of the loop, so both D and E, our counter, is 0, right? And all we got to do is now load the sum and display it, right? But remember that the machine works in hexadecimal number system, so we have the result now in 1 and 2, 1 byte we said, right, but in hexadecimal. So for display we want to convert it back to decimal, and for this we are now moving the value of the value in the 1 register to D, and the value of the 2 register to E, and then use a hexadecimal to decimal conversion, which is also built in opcode. So let me do this, and for this we are copying the register. 0 is move, or basically it's a copy, right, from source to destination register, right? So I'm copying the 1 register to D, I'm also copying the 2 register to E. And why do I have to do this? Because the conversion opcodes, decimal to hexadecimal and hexadecimal to decimal, only work in the DEF registers, right? So this is where it expects its arguments. And previously we used FO4 to convert decimal to hexadecimal, right? And now we're using FO3, which converts hex to decimal, right? And after that, sometimes the keypad is bouncing a bit. Of course, this machine is a bit old, right? From 1981, that happens. So FO3 again. In particular, the 3 is a little bit bouncy. And then now we have the decimal result in DEF, and all we got to do is display, basically turn on the display again and display 3 digits, right? F for display opcode, 3 digits, and then start at register D. So we are going to see D register, E register, F register on the display, right, from right to left. So as I said, D is like the lowest value position, right? Then comes the 10 position, then comes the 100 position. So yeah, and so now we simply put in one more wait for keypad input, right, and put this into register 0 or any other register, doesn't matter, just to keep the display alive, and so that it displays the display value until we hit a button, and then we just start the program again. C is go to, right, unconditional jump, and 00 is of course the start address. Alright, let's see if we can actually run that program. So maybe one more check that we entered everything correct. FO8, F2D, FFE, FFD, FO4, FO2. Yeah, looks okay to me. Good. Halt next 0, 0 and run. So we are now at this point, right? So it displays registers D and E, and I can input now the value for the 2 digits. So let's use 0 for the ones and 3, right? And the result, of course, should be 6. And there you go. And now, unlike the CP1, right, I don't have to, restart the program, change memory values or whatever. So all I have to do is, we are now, it's waiting for our keyboard input now. All we have to do is do another round, and let's use 10, and we're getting 55. You can tell that the machine is quite a bit slower, right? And as I said, it's about a factor of 10 or so slower than the CP1. And from our previous experiment with the CP1, we know that the highest value that fits into 8-bit, right, is 22. And yeah, that takes, a few seconds, but the result is, of course, 253. And so that's correct. So and for 23, unlike the CP1, which gives an overflow error, then it simply doesn't display the correct result, right? Because you have an unhandled overflow, and you would have needed one more carry overflow to register 3 to keep track of the sum, right? So by the way, this is, you can tell that TI definitely had a say in designing this machine, right? So my classic TI-30 LED, bubble LED display calculator, right? And to double check, basically, if you know the formula that Karl Gauss came up with for this problem, right? So it's basically n times n plus 1, right, divided by 2. So for n equals 3, you get 6, right? And for 10, oops, and see, this has the same problem that the keys are bouncy by now, right? For 10, you get 50, and for 22, you get 253. All right. So what does it actually take to extend this to more than 8-bit, right? So that we can, for example, compute the sum to a max value up to, say, 999 or so, right? So we can still display it on 3 digits on the display, right? And so I've prepared a little extension of this program, right? And so this is my re-implementation of the Microtronic, right? You can find the project on GitHub. So it has some improvements. For example, it has something like an EEPROM, right? And I can store programs in there. And let me load the program that I already prepared, which is a simple extension of the program that we just entered together. So I've loaded this program now, right? And let us step through this and just show you the differences, right? So it's it's very authentic, right? So the look and feel and the programming experience is, I deliberately made it very close to the original, right? I also made other versions which have, more fancy OLED displays and things like this, but this is really the version which I like the most, right? Because it's so close to the original. Again, it starts with clearing the registers, right? Then it does the keyboard input for the n value as just discussed, right? Then it does the decimal to hexadecimal conversion, clears the display. This is where the loop starts, right? So we add the lowest value digit to the sum, right? We do the overflow into the register 2. But now we also do the overflow into one more register, right? Because there can, of course, be ripple effect. So if this register already has, say, F, right? And this register also already has F, right? And you add 1, right? Then not only do you have a carry ripple overflow to this one, but also to the next one, right? And by basically using a sequence of FB 2, 3, 4, 5, 6, you can basically have a ripple carry overflow counter, right, of arbitrary lengths, right, until you run out of registers, of course. But here we now have a 12-bit counter, right, And so then this basically is one change, right? So one more carry overflow to the 3 register. And then we also have to, of course, add the next highest value registered of the counter to the sum, right? And again, this can now also overflow in the 3 in the register number 3, right? So basically 2 instructions more, right? Carry overflow, and then the rest is identical. We decrement the counter, we do the underflow of the counter right into the next value position register. Then we check if the counter is 0, right? And if not, if it's 0, then we move now 3 of the registers to the conversion registers DEF. So this is as like in the previous version, right? But now we also move the 3rd register for the sum to the F register. We do the hex to decimal conversion and display, right? So it's really the same program, only with 3 instructions also added, right? And that gives us now the ability, basically still works for 10, right? Should be 55, right? By the way, we can also run this a little bit faster. So this is the max speed of the emulator, 22, right? And you see that this is a bit faster. So let's actually do this at the same time here. 2. Yeah, that's a bit faster. But now the max value is something like, how about 40? 40 is already 820, right? How about 44? So the highest value we can compute the sum up to is 44. After that, you know, we would need 4 digits, right? So yeah, okay. So now you have a good understanding of how the Microtronic can be programmed, right? And what its machine model is, and that it is actually quite versatile. And unlike the CP1, you can chain registers together and create larger than 8-bit values easily, right? And of course you have more control over the display, and you can do things like keyboard input, keypad input at runtime, etc. But as I said, I mean, I'm not going to bash the CP1 here, right? I think this is, as I said, a very nice cherished item in my collection, right? And I'm happy to have it. It's just different, right? Alright guys, thanks for watching. Until next time. Bye.